Okay, so today, what did we do last time? We'll just quickly review. So we started off with our 3D data, and then we did some normalization because the problem was we're trying to distinguish gray from white matter, but they're only like 5 or 10% different from each other. But then there's variations in brightness, which might be 30 or 40%. So we have to deal with, sort of normalize it. And then we did some kind of, we used to call it flossing, like dental floss. So we do some kind of filtering, filter, to filter the data to get rid of the little, we used to call them wormholes. So because if you have like a sulcus like this, and then suddenly there's a little attachment to the other sulcus on the other side, to the other bank of the sulcus, you end up with something that looks like this. You get this little wormhole between the sulci. Sorry, there. There we go. Yeah, so this thing is so we have our wormhole filter, because the problem is we actually have to deal with 10 million voxels, and even if we mess up on 1,000, that's going to be too much to fix by hand. So then we did a fill, sort of to fill up to the white matter. And why did we try to just fill up the white matter? The reason was because the white matter doesn't approach itself as closely. So if you look at the cortex, it looks like this. And the gray, if this is the white matter and this is the gray matter, this surface doesn't get as close to itself as this surface does. So that you might think at first, why don't you just go try for the cortical surface, because that's well defined. But it turns out it gets very close to itself, and especially if you look at my brain, there's a little space in there. But if you look at your brains, there's almost no space in there, because your brain is nice and full and plump when you're younger. And so it's actually quite hard to discover this surface, because it often doesn't even hardly get dark at all in between it. It's so close to itself. And so that's the reason why we're trying to just fill the white matter and not the gray matter at the beginning. So we fill everything up, and then we turn it into a surface. And remember, suddenly we're in this other land of a list. It's just a list of vertices and who their neighbors are. So it's a fundamentally different data structure. So make surface, and this is 2D list. 2D list of vertices. No, it's not 2D. So we'll just call it it's actually just a 1D list. So it's a list, vertices, and then faces. Which vertex is in each face, and from that information, then you can sort of figure out for each vertex who its neighbors are. So here's a little patch of the surface. So this, vertex number 12 knows that it's connected to vertex 11 and vertex 3 and vertex 17. So that's our representation of the surface. And one thing I didn't mention last time, why go through all this trouble? Well, one of the big advantages of it is that you can see everything at once. So if you look at a 3D representation of the brain, it actually only shows you about 30 or so percent of the total surface area, because the rest of it's down in the folds. So if you just have a normal 3-dimensional picture of the brain like this with folds, you're only seeing 30% of the surface. And so if we could sort of inflate that up and get rid of all the folds and just put a mark as to where the folds used to be, then we could actually see all the data at once. And so that's one really big advantage, rather than either looking at it from the surface and you can't see everything, or just cutting sections through it and then you've got to look through 20 sections and they look different in different people. So there's a lot of just sort of cognitive ease of processing the data reason to actually make a surface, because you can see everything on the lateral side. You have to turn it over to see on the medial side, but that's much better than having to look through 20 slices. So that's one major reason. So even if you do everything in 3D, you still often want to display it on the surface so you can see where stuff is. So what we want to talk about today is how do we manipulate that surface? So once we have the initial surface, which was just really the faces of it was just it was the faces of these filled 1 by 1 by 1 voxels. So here's our surface like this, etc. It's just a tiny bit of it. So there's 4 filled voxels, and then outside of them, coming this way is just air or not filled, but the surface is defined as the boundary between filled and not filled. So there's another voxel, say, out here, and that voxel is not filled. So that guy's not filled. And so what we're looking for is the boundary. The surface is the boundary between filled and not filled. So this guy is filled, not filled. So now that we have that surface, it's a kind of it's a real rumply surface. It's not a very nice looking surface. And so how do we fix that? And then how do we find the other surfaces like the peel surface? Or how do we inflate the brain? And so what we'll talk today about is just some of the math of how we manipulate the surface. And this particular math method that we're going to talk about, where we define some kind of error function and then we take the derivative of it, is very general. So it's not just for this. It's kind of something that can be used if you're reading any kind of applied mathematics paper, you'll often see something like this. So I'll just say one other thing about it is that this is not the way we developed it. So when we developed this, if you actually look at, my PhD was originally in philosophy of science. So if you look at sort of the history of science, what often happens is people do something, they figure out something, and then later on, years later, they come back and say, and they phrase it in a more scientific way that actually doesn't really reflect how people discovered it in the first place. And that's the case here. So what I'm describing to you today is kind of how we reformulated this properly mathematically. This isn't how I actually sort of got it. We originally got it just by thinking about little springs on the surface. And then now it can be sort of formulated in a proper way, and I'll describe the proper way, but it's not the actual way that it was originally done. So that's an important thing to keep in mind. So you don't have to be like overly fussy. Eventually when you publish something, you can be as careful as you want. But if you're sort of on the cutting edge, you can often sort of take some chances and just try something, and then later on you can sort of straighten it up and make it sound more scientific. So let's start off with sort of our error function. So what this thing is, this is something that tells us, so this is something that we're trying to minimize. We want to minimize the error, and so we're going to define different kinds of errors relative to the vertices on this, the position of the vertices on this surface. So for instance, if we want to smooth it, we're going to have a smoothness error. So this is the total error. So the total error, and that's just a number, so that's a scalar. So total scalar. So it's just a single number. Total scalar error. So it's just one number, and it's how much error do we have total, and that's equal to some error that is, we'll call that one tangential. So like error sort of in this direction, and then we've got some a little knob here that controls the relative power of these different errors. So this guy, you could think of this guy as multiplied by 1. This guy's weight is 1, and then this lambda normal is like how much do we weight the normal error. So the normal error is the amount of error of like smoothness. So if you look at this vertex here and the surrounding vertices, they're not very smooth. They're kind of rumply. It doesn't make a nice sort of smooth skin of the surface. So we can measure how unsmooth we are, and then we weight it by, we want smoothness to be less important than the tangential error, how the vertices are distributed along, parallel to the surface. So, but then we're also refining it against data, and so we want another error for an image. So we might have an image in there, and so here's the image error, and we'll define what that is. And so, for instance, we might want to make the surface go to the gray-white matter border, in which case we've got sort of an image embedded in this surface mesh, and so and we want to move the vertex to sort of refine it and make it closer to the gray-white matter border. So so that's our total error, and this typically, I think, if that one was 1, this one might be less important than the tangential, and this one might even be less important than the. So these are things just done empirically. So we just run the program and see, oh, that surface looks a little bit too rumply, so I'll turn up the importance of the normal meaning perpendicular, of the normal error. Or that surface is really smooth, I can turn that down. Or it didn't agree with the data, so I'll turn the data error up a little bit. So basically, so that's our starting equation. So now we want to define each of the parts of it. And so the parts of it are, I'll leave that one up there at the top there. So the parts of it are, we'll first define the errors before we figure out how to reduce them. So the first plan is, I'll start off with the normal error. That one's a little bit easier. So I'll save some space to draw on this side. Okay, that should fit. So here's the normal error. So the normal error, to do this, we have to kind of like make a picture of just one vertex and its neighbors. So that's what the picture is here. So here's one vertex, and say this guy just has three neighbors like this. Okay, so there's 3 neighbors, and here's one vertex. And so this is the center vertex. So this guy is it's a vector. So that's a vector center. Okay, so that's our center vertex. So what does it mean that that's a vector? So what that means is somewhere down here there's the center of the coordinate system. So say this is the center of the coordinate system. So then this guy is actually you can think of this guy as actually a vector. You know, it's somewhere in three-dimensional space. That's what what it means when we have an R like that. So somewhere in three-dimensional space, we've got a vector, and the neighbors are also vectors. So here's a vector going to a neighbor. So this guy is we're going to have these things in our equation. So this is the R vector to a particular neighbor. Now there's multiple neighbors, but that's one neighbor. Okay, and then that's kind of inconvenient dealing with these vectors that are all going back down to the center of the coordinate system. What we really want, for the purpose of sort of calculating these local errors, is the difference between those. And so this vector here, that's another vector. That's the vector that is equivalent to. There's a typo in the notes. I'll fix it next time. But so this guy is basically, so from the center out to one of the neighbors is basically the neighbor vector minus the center vector. So this is just basically, if you just take the neighbor vector, and then vector subtract it from the center vector, you get that one. So how does that work? Well, here's neighbor, and then we take center and we negativize it. So we would take center, put it over here, and so we go this way, and then tip to tail go this way. So we end up with that vector, and so that vector is the vector difference between neighbor and center. And there'll be another one of those, over here, and there'll be another one of those, over here. Okay, so good so far. So now we need to define the normal. So this guy will have a normal vector. So this guy is, and that vector will be called, so that's normal vector of the center. And what does that mean? That just means the vector that's perpendicular to the surface. And so how would you compute that? You might do something like do cross products with all the surrounding guys, and each cross product will generate a perpendicular. And then if you add them all up or average them all, you'll end up with a vector that sticks out. And typically the length of that is set to 1. Length equals 1. So if you measure the length of that, you set that to 1, and then you kind of have a standard little vector at each vertex that points out and is perpendicular to the local surface. Okay, so good so far. So what we're trying to do is sort of figure out the error in normal, and error meaning the fact that it's curved, because if there's no error, it would be very flat. Now, of course, it can't be completely flat because the brain is kind of like a balloon, but it could be really not flat, like zigzagging up and down. So here's how we define the normal error. So we define the normal error as 1 over 2 times the number of vertices. These are sort of normalization things, because we're going to take it a derivative, and the derivative has a square in it, and so we're going to end up with a 2, and so we divide by 2 in order to get rid of that factor. So that's just to sort of make the equation neater. And then this single error number is the sum across all the centers. And then for each of those centers, it's a sum across all the neighbors of the following thing. So what this means is, for every center, when you're at one center, go to every neighbor and then do what's going to be what I'm going to put here. And so so what is the error defined as? It's defined as this normal vector for the center dot producted with the neighbor vector. And so what does that mean? Sorry, so here's where there's a typo in there. It should be neighbor minus center. Okay, and then that whole thing is squared. So what's going on there? So this is a dot product between the vector that goes to the neighbor and the normal vector. And so what is a dot product? A dot product is, you can think of it as a projection. So you can think of it as, basically we take this vector and just project it onto that normal. And then we get this thing here. That's the projection or the shadow of this vector onto the normal vector. And since the normal vector is 1, the dot product equals the projection. If the normal vector wasn't 1, the dot product wouldn't equal the projection. But if we set it to 1, then it just represents the shadow of this vector on that normal vector. And so that pretty much tells us how bent that vertex is, because if the normal vector is like this and that vertex is like this, it's almost flat. If it's like that, it's really not flat. So the bigger this dot product is, the less flat it is. So that's how we're defining it. And then why do we square it? So we square it because then we get rid of the sign. It just measures a total error. It doesn't tell us whether it's whether this was a positive or a negative thing. So it just says how much is the curvature, and we don't care whether we're concave or convex. We just know we're wrong. We'll get back to how we actually figure out the difference between convex and concave. Okay, so that one's pretty good, pretty straightforward. So you basically just project, this is dot product, with a normal vector that equals 1. So there is just a project. So project, find the shadow of the neighbor vector onto the normal vector. Okay, so then, so that's the normal vector. The tangential is a little bit more complicated. So this is tangential because now we have sort of 2 other dimensions. And so the way the tangential works is we first need to define a coordinate system perpendicular to the normal vector. And so let's draw that in a different color. So we have, so here we have 2 vectors at right angles to each other, and both of them are perpendicular to this normal vector. And what those things are doing is those are defining a 2D coordinate system for us that's parallel to the surface, whereas the normal vector is perpendicular to the surface. And so what are those called? So those are called, we'll call this the t vector. So this is the t vector that is for, say, the x-coordinate, and that's for the center vertex, because there could be the same thing for the other vertices. And then this guy is the t vector for the y-coordinate for the center vertex. Okay, so now we didn't say how we get that. One way to get that is we could take the eigenvectors of the surrounding vertices, of the cloud of surrounding vertices. There might be more, it might be 7 vertices. So if you have 7 vertices around the current one, take the eigenvectors of that and basically fit an ellipsoid to it. And the normal vector will be the 3rd eigenvalue with the smallest value. And then these other 2, the first and second eigenvector will define 2 perpendicular to each other coordinate system vectors, sort of the x and the y coordinate system vector. That's how you actually do it mathematically, but you can sort of see what's going on here. You've got a normal vector that's perpendicular to the surface, and then you've got these other two ones that are parallel to the surface. But since we got 2 dimensions on the surface that way, we need 2 of those. We just need 1 for the perpendicular. Okay, so once we have those, then we can sort of project onto those as well. And so here we, 1 over 2 times the number of vertices. And so now we're summing over all the centers again. And we're summing over all the neighbors again. And now we've got two things, and so they look pretty much like the one up above. So we've got our x local parallel coordinate system vector, and we're projecting on this same vector. We haven't said why we're doing that yet, but I'll get to that very soon. Center, okay. And then we've got the same thing for the other coordinate. So what is the goal of this? So the goal of this basically is to sort of figure out how minus our center. So the goal of this is to figure out how squished up the surface is. So we call this, we'll call this squishing. Squishing. So this basically was curvature. So flat is low, error, and curved is a high number. In this case, it measures the squishing. And what is the squishing? The squishing would be something like this. If you've got, vertices that look like this, so say here's the vertex and its neighbor. Well, let's draw, there can be more than 3, so let's just draw more than 3. So say you have a situation that looks like, here's the center, and then here's the surrounding vertices like that. Okay, so here's the surrounding vertices like that, and then here's the center going to all the neighbors. So that guy is that guy is a little squished. What we would like is something that has everybody sort of about the same distance away like that. So this guy is squish. Especially, I'll put this one very close to there. So this guy is squished, and this guy is not squished. So that's my technical term for it. So the idea is you want to sort of have the surface have all the vertices distributed sort of uniformly around the surface, and not all sort of squished up. Because you can imagine over the surface, there might be an area where they're all like squished in together, and we don't want that. We want them all nice and equally divided. So what this does is this measures how squished it is, and so we want to minimize squishing. Okay, and then at the same time, we need a third thing, which is we need to measure which way we should go depending on what image we've got in there. So on top of this whole mess, there's actually an image. So let's just draw that image here. So here's an image. So we've got an image there too. I just drew it as 2D, but it's actually a 3-dimensional image. So this surface is floating inside the image. And so here's, that's the center vertex. And so the center vertex can say, what voxel am I in? So here's the voxel. Here's the voxel so this is, voxel our center is in. So this guy is that that one right there. So that voxel, so it's sitting, this center vertex right here, let me just try, it got covered up. So that center vertex is sitting just inside the corner of that voxel. Okay, so, and maybe that's not the voxel we want to be in. Maybe there's, this way, there's something that looks more like the gray-white matter border. And so now we have another error that says, how far are you away from where the surface is supposed to be? So that's what this one is. So this one is 2 times number of vertices. And then this one's also times all the for all the centers. But in this case, what we're doing is we're just looking at the error in the image. And so what is that? So the error in the image is going to be the image value, the target image value. So say we're trying to look for the gray-white matter border. What is the brightness of the gray-white matter border? That's what this is. And this guy is for the center vertex. So that's that center vertex sitting inside this voxel here. So this guy is the target, what we want that to be, and then we're going to subtract off what it actually is. So here it actually is. So at this point in the 3D data set, what is the actual value? So that might be, if we're aiming for the gray-white matter border, which we say is like 110, and so this would be 110, and this one might be 90. It's too dark, and so we want it to be sort of closer to 110. So that would be 110 minus 90 is a positive number, and then we square that. Basically, what this will do, this will go up. This number will go up the further you are away from the number that you're trying to get to. So those are our three definitions. Let's separate them so we can see. I drew them really close to each other so I didn't have to erase anything. Okay, so now we have to somehow figure out how to minimize those errors. So how do we minimize the errors? So this is the part that I said this is a very common method of a very common mathematical method. So what we do is we take the derivative of the errors, and then we try to figure out, kind of like the landscape of the errors, and then figure out which way to go to reduce. So a simple derivative is something like this. Here's a function, and what is the derivative at a point? The derivative at a point is just the slope. It's just the slope. But here we've got a lot more variables, and so the generalized derivative is called the gradient. And so let's just generalize to two. That's one dimension. Let's just do 2 dimensions. So say you have a 2-dimensional space, and now imagine there's some sort of surface in that 2-dimensional space like that. So that's a surface in the 2-dimensional space. Okay, let me put the space back in. So here's the space. So what we're trying to represent is that surface is kind of floating above the 2-dimensional space. So what are the dimensions? We've got dimension 1 this way, and dimension 2 this way. Sorry. This way. Okay. And so then what is up? So up is error. Okay, so all we've done now is we've just changed over to we've got 2 dimensions instead of 1 dimension here. So here's, dimension 1. And then here's error, j. And so if you only had 1 dimension, you would say take the derivative, and then if you want to reduce the error, change dimension 1 to go downhill. So what we're doing instead is we have 2 dimensions. And so if you have 2 dimensions, then we have to take what's called the gradient. And what the gradient is simply the steepest uphill direction. So if you go to some place on that function, there's a way to calculate, a straightforward way, just by looking at the neighbors, which is the steepest uphill direction. So that's what the gradient is. So this guy is gradient equals steepest uphill. Okay, so that's what we want to do. So how do we do that? So let's do the image one as the easiest one. Oh, sorry, one last thing. So obviously the steepest uphill direction is the way to make the error the worst. And so what do we want? We want the exact opposite. We want to go the other way. And so if we just take the negative of that gradient vector, so we calculate the gradient, take the derivative, which is another way of saying take the derivative of a multidimensional thing, calculate the gradient direction, take the negative of it, that's the way that we want to go. It's analogous to this direction. That's the way we want to go to reduce the error. So this is an error minimization problem. So if we can calculate the gradient at each point, then we can figure out which way to reduce the error and fix this problem. So how do we write that out? So we write that out as the negative of the gradient of the error. So that just sounds like absolute hell, but it's actually not too bad. So that guy's a scalar, and this guy is the center vector. And so what we're trying to figure out is the negative derivative of these j functions. And it's a partial derivative, and what does that mean? So that means we're only concerned about changes in the center vertex. We regard everybody else as, so this part is regard all but our center as fixed. So we don't care about them. All we care about is we'll just assume those guys are fixed. Which way should we move the center? That's the only variable. Which way? That's what the partial derivative means. Which way should we move the center, assuming the other guys are fixed, in order to fix our error? And so if you take the derivative of this guy, or you take the gradient of this guy, this is like it's called the directional derivative, because when you do more than one dimension, you end up with a vector. So this is the directional derivative equals gradient. We'll talk about gradient next time also. So directional derivative gradient. And then take the negative of it so that we go downhill. So what does that look like? So that looks like, so here's our sort of weight knob. There's our weight knob. And times the function here, the same function here. So when we take the derivative of this, this is some functions squared. And so how do you do that derivative? Well, like the derivative of x squared is basically 2x. So you take the derivative of you take the constant from the power, move that out in front, and then you reduce the power from 2 to 1, and you end up with 2x. So that's kind of what we're doing. So there's going to be a 2 there. The 2 will get canceled out by this 2. And then we have to sort of like do the chain rule. So we have to sort of take this thing, and that's going to just reappear. And then we take the derivative of it and multiply it by this thing. So that's the rules for taking the derivative. We have to sort of, we've got some functions in here, so we have to take derivatives of them. So basically, the derivative is just equal to the center minus this thing that we had before, not squared now. And then we have to take the derivative of this image function. So the derivative of this guy is going to equal the gradient. So there's the gradient symbol. The gradient of this image. And so what's the gradient of this image? Just multiplied by the gradient of this image. So this is the derivative of this guy. Chain rule derivative. So now we actually have something that makes really intuitive sense, believe it or not. So what's going on here? So what's going on here? So what's the gradient? So the gradient is just the direction in which the image changes the fastest. And so say you've got some, gray and white matter. So what's going to happen is, here's all the voxels in the white matter, and they're going to be pretty bright. So here's all the voxels in the, so these guys will be pretty bright. There's some voxels in the gray matter, they won't be as bright. So when we take the gradient of, this is the gradient of this image, it just says, what is the direction where the voxels change the most rapidly? And what is that direction? Well, it's going to be, for this voxel right here, it's going to be that direction. Because if you go in that direction, that's how you get the brightest. If you go in that direction, that's how you get the dimmest. If you go in this direction, you don't change. So the steepest uphill direction in the image is the direction, 3D direction in the image that you go in order to get the most bright. And you can just calculate that from your surrounding voxels. So what this says is, this is how far off you are. So this is, how far off. And this tells you the direction. So this guy's a vector, which way to go. So now we have a way to fix our problem. So if our problem is that we're far off the target, then we should go a long distance in the direction of the gradient, because that will sort of like make us reduce our error more. If we're just about right, then this will just go to 0. So say we just happen to be in a voxel that was just exactly what we wanted it to be, the target. Then the target minus the voxel that we're in is 0, and then we don't go anywhere. That's exactly what we want. We just want to figure out which way should we go in order to make this vertex be inside a voxel that is more like our target. So this guy will sort of like make us go in the direction of a particular tissue type. So that's an easy one. So now we have a slightly harder one. I won't draw the last one out. It's very similar to because we're sort of going a little low. So we're going to add another vector. So this guy is a vector. So this whole thing is a vect. This is a vector. It tells us which way to go. So now we're going to add on another sum over all the neighbors. But now we're doing the curvature one. So we've got our weight, our normal weight. How important should we make this vector? That's what that says. And then when we take the derivative of normal, which is the next hardest one. What do we get? So we got the same thing going on. We've got to deal with the chain rule. So first we write out the thing, So it's exactly the same as it was before. So here's the neighbor vector minus the center vector. And then it's no longer squared. So remember, it was normal. It was squared here. But since we took the derivative of it, I think I left out some squareds there. Oh, yeah, sorry. There's some squareds. Okay. Since we took the derivative of it, the power goes down 1, and so this is no longer squared. But now we have to go inside this thing and take the derivative of this thing. And so when we take the derivative of this thing, that's a constant, that's a constant, that's a variable. So that means we have a constant 1 times a constant 2 minus our variable. We can write that out as constant 1 times constant 2, minus constant 2 times variable. We just distribute that. When we take the derivative, the constants go away, and the variable gets reduced in power to power 0, which is 1, and so the end result is just constant 2. And so negative constant 2. That was my typo. And so if you look at this derivative, we've got to now multiply it by negative normal vector of the center. Okay, so, and then there's another term for tangential, but I'll, et cetera for tangential. It's very similar, but I won't clog it up. I'll just leave that. Let's just see how this one works. So this one works by, so we look at this thing here. So this thing here is pretty much that projection, this projection onto the normal. So here's our projection onto the normal. And that projection on the normal can be positive or negative, because if it's a concave surface, then the projection onto the normal is going to be sticking out of the surface. If it's a convex surface, the projection onto the normal is going to be going into the surface. So that could be a positive or negative number, depending on whether it's convex or concave. And then we're multiplying it by a vector. So again, this is the same thing. So this guy is, this is a vector, length equals 1, and this guy is a weight. This is a, how far off from flat. So how far off from flat are we? Are we almost flat, in which case we don't have to move, or are we really convex or really concave? And then we're essentially, this tells us which way to go. Now, this tells us to go in a negative direction. And so if we were concave, like this, that would make it worse. That's kind of exactly the kind of logic we have, because remember, there's a negative here. So this says, like, go the other way. So this one, remember, tells you what is the worst way to go. And so the worst way to go is to make you more concave, and we take the negative of it and make you less concave. So it all works out in the end. So the bottom line is, you can use this to refine the surface. So you start off with this very blocky surface, and you can make it nice and smooth. You can use it to inflate the surface. If we add another term that sort of that says, pay no attention to the data. So turn this image thing completely off. In which case, it will just try to make the surface smooth. That's how we would inflate. Or we could try to make the surface go somewhere else, like find the peel surface. So if we started off reconstructing this surface here. So here's our estimate of this surface here. But what if we want the peel surface? In that case, we would turn our image so that it tries to make the surface float outward until it runs into the darkness at the edge of the brain. And then we'd have to deal with this, like, you have to stop it from going through itself. That's a little extra complication, but But basically, you can use this to refine the surface and discover the peel surface. So, so this is the absolutely simplest. Now, when you see this, you say, how could this be simple? This is the most brain-dead way of doing this. And the reason is because we're strictly looking local. So all these equations, they only look at the neighbors. They have no idea where they are. And so this won't work very well if for instance, we are completely, say the surface was completely in the white matter. It's not going to work very well because it'll go, which way can I go to get toward the gray matter? And they say, like, no way looks good. So this is a very primitive method. It works really good if you start off pretty close to the gray-white matter. It can refine it. But since it has no conception of where anything else is in the brain, it's strictly looking at its neighbors, just its neighbors. So there's 150,000 vertices, it's just looking at the neighbors. It's a very local method. There's better ways to do this that are much more computationally intensive and more complicated. But this one is very computationally practical because we only have to sort of look at each neighbor. And so how do you do this? One last minute. So how do you actually sort of run this? What you do is you calculate this for each vertex without moving any vertex. So you just say, let's go to this vertex, look at its neighbors, figure out which way I should go, but don't move. Go to this guy, look at all its neighbors, figure out which way to move, don't move. Do that for everybody. And then once you've done that calculation for everybody, move everybody a little bit. Then just do it again. And so what will happen is the surface, if you're trying to refine this surface, the surface might have started off blocky like this. So here's those original classified voxels, something like that. So it'll start off blocky like that, but it will quickly say, this has got too much curvature over here, and so this guy's got to go that way, and this guy has to go that way. This guy has to go that way, and this guy has to go that way. And so what you'll end up with is a nice refined surface. So that's how FreeSurfer makes these nice smooth surfaces, starting with just a pile of blocks. Okay, Stan, I think I've overstayed my welcome. We'll stop the recording now, and I'll take some questions after the recording is off.